The universe is a vast, mysterious expanse that has always gripped human curiosity. Around 13.8 billion years ago, from the depths of absolute nothingness, a grand cosmic event occurred, the Big Bang. In the blink of an eye, the empty void transformed into the universe, birthing everything we see and know today. This sudden miraculous emergence set the stage for the wonders and mysteries that filled the cosmos. But how did this sudden change happen? Scientists gave a lot of thoughts over this. It's a big deal in physics and philosophy. Our whole grasp of how the universe works depends on cracking this puzzle. We've been digging for answers, but we're still stumped about the how and why of the universe's birth. This cosmic mystery has a big impact on what we know about the world around us. It touches on how things work, what makes stuff happen, and why things are the way they are. Even with all our smarts and fancy tools, we're still in the dark about a lot of it. People have been trying to figure this out for ages. It's not just about satisfying curiosity. Understanding where it all began could revolutionize our view of reality. But for now, we're left with more questions than answers about the universe's grand entrance. Join us on this enigmatic journey to uncover how the universe began. Later in the video, we'll also explore the ways our universe might meet its end. In the very first moments of its existence, everything we see today, every star, planet, and galaxy, was packed into a space smaller than an atom. This was the beginning, and it was marked by an era known as the Planck Era, a period lasting just a tridecillionth of a second. During the Planck Era, the universe was incredibly small and extremely hot. The physics that we are used to seeing today simply did not exist. Instead, all was regulated by quantum mechanics, the science of things incredibly small. At this scale, the ideas of time and space, as defined by human beings, also crumble into dust. At this point in time, everything in the universe was condensed and hot beyond human imagination. The temperature at the Planck Era was so high that it attained what is known as the Planck temperature of about 1. Undefined for the sake of comparison, let me note that this is orders of magnitude hotter than any star core, and even hotter than the interior of the most powerful human-made particle colliders. At these temperatures, the basic forces of the universe, such as gravitation, electromagnetic, and nuclear forces, were tightly combined into a single force. The Planck Era represents the closest we can get to the true beginning of time and space. It's a period that lasted for just 10 raised to power minus 43 seconds. To understand how short this is, consider that a second is divided into 1 trillion parts. Then divide one of those parts into 1 trillion again, and then 1 trillion again. That's still not quite as brief as the Planck Era. During this time, the universe was so dense that it was difficult to distinguish between different particles or forces. Everything existed in a kind of quantum foam, where particles popped in and out of existence in a chaotic dance. Because of this extreme density and energy, the universe was in a state of rapid expansion, known as cosmic inflation. Inflation caused the universe to grow exponentially in size, from something incredibly tiny to something much larger, in an almost unimaginably short amount of time. One of the biggest mysteries of the Planck Era is how gravity works on such small scales. Normally, gravity is described by Einstein's theory of general relativity, which works well for large objects like stars and planets. But in the Planck Era, everything was so small and energetic that general relativity no longer applies. Instead, we need a theory of quantum gravity, which combines quantum mechanics and general relativity. However, physicists have not yet fully developed such a theory. At this time, the universe was not as developed as it is today. It is the epoch when the rate of activity and density were extremely high, and the temperature was billions of degrees. In the universe's early stages, the temperature was extremely high. Everything was in a plasma state, and particles were moving at very high velocities. Imagine a period when the rules of physics we are taught today had yet to be formulated. One of the most intriguing elements of this period was the idea of symmetry. During the Grand Unified Period, the universe was also mirror reflection symmetric and contained an equal amount of matter and antimatter. This is one of the symmetries that are central to physics, and it helped to define the nature of the universe. As the universe expanded and cooled, this symmetry started to be broken. This breaking of symmetry led to the formation of the fundamental forces of nature, the forces we know as gravity, electromagnetism, and the strong and weak nuclear forces. These are the forces that are said to be containing the universe and controlling the movements of particles. The other significant element of this period is the notion of integration. This was encountered in the Grand Unified Era, whereby the forces of nature were combined into one force. This implies that the universe was run by a single natural law instead of the four forces of nature today. It is believed that as the universe expanded and cooled, this singular force started breaking into what is today seen as different forces. This process of union and division is an integral process of the existence of the universe, and it is still a mystery. Another noteworthy feature, characteristic of the Grand Unified Era, is the participation of particles. In this period, there were particles in the making, and these particles were highly energetic in nature. Indeed, the energies involved were so colossal that they produced particles that are nowadays absent from the universe. These particles, known as X-bosons, were incredibly heavy, with masses millions of times greater than the proton. They were responsible for mediating the fundamental forces of nature, and they played a crucial role in shaping the universe. As the universe continued to expand and cool, these X-bosons began to decay, giving rise to the particles we see today. This process of particle formation and decay is still not fully understood, and it's an area of active research in the field of physics. Previously, we explored the Grand Unified Era, when the universe was full of energy and density. As it expanded and cooled, the Electroweak Era began. During this era, which lasted from 10 raised to power -35 to -10 seconds after the Big Bang, the strong force decoupled from the electroweak force, releasing a tremendous amount of energy and triggering a sudden rapid expansion known as inflation. This inflationary period was so rapid that space expanded more quickly than the speed of light. As the universe expanded, extremely energetic interactions took place, creating elementary particles such as photons, gluons, and quarks. These particles were the building blocks of the universe, and they would eventually come together to form atoms, stars, and galaxies. Photons, which are particles of light, were among the first particles to be created during the Electroweak Era. These particles were incredibly energetic, with energies that were millions of times greater than the photons we see today. As the universe expanded and cooled, these photons began to lose energy, eventually becoming the photons we see today. Gluons, which are particles that hold quarks together inside protons and neutrons, were also created during the Electroweak Era. These particles were responsible for mediating the strong force, which holds quarks together inside protons and neutrons. As the universe expanded and cooled, gluons began to interact with quarks, forming the protons and neutrons that make up atomic nuclei. Quarks, which are the building blocks of protons and neutrons, were also created during the Electroweak Era. These particles were incredibly energetic, with energies that were millions of times greater than the quarks we see today. As the universe expanded and cooled, quarks began to come together to form protons and neutrons, which would eventually form atomic nuclei. As the Electroweak Era came to a close, the universe underwent another significant change. The electroweak force, which is a combination of the electromagnetic force and the weak nuclear force, began to separate into two distinct forces. This separation marked the end of the Electroweak Era and the beginning of a new era in the universe's evolution. It was a time of rapid expansion and particle creation, a time when the universe was still in its infancy. During this era, the fundamental forces of nature were still taking shape, and the building blocks of the universe were being created. As we continue to explore the universe's evolution, we'll see how these particles and forces came together to form the universe we know today. Just after the Electroweak Era, the era of elementary particles began, which occurred between 10 raised to power minus 10 seconds and 1 millisecond after the Big Bang. During this period, the universe was a particle soup filled with quarks, antiquarks, electrons, positrons, and other particles and antiparticles. These particles continuously swapped mass for energy through matter-antimatter collisions. As the universe continued to cool, the temperature dropped too low to recreate pairs of particles from photons. Consequently, particles and antiparticles continued to annihilate each other without being replaced. This process significantly reduced the number of particles in the universe. However, a slight asymmetry between matter and antimatter allowed matter to dominate. This asymmetry, though tiny, was crucial because it meant that matter became the universe's primary ingredient, shaping everything we see today. With the temperature continuing to drop, the strong nuclear force started to play a crucial role. This force began drawing quarks together to form protons and neutrons. These particles are the building blocks of atomic nuclei, which later combined with electrons to form atoms, the basic units of matter. The formation of protons and neutrons marked the end of the chaotic particle soup and set the stage for the next phase in the universe's evolution. The elementary particle era was a brief but critical period in the universe's history. The interactions and transformations that took place during this time laid the foundation for the matter-dominated universe we live in today. The dominance of matter over antimatter ensured that stars, planets, and galaxies could form. Without this asymmetry, the universe would have been a very different place, potentially filled with equal parts matter and antimatter annihilating each other, leaving behind a barren cosmos filled with energy but little structure. Following the elementary particle era, the universe entered the era of nucleosynthesis, which lasted from 1 millisecond to 3 minutes after the Big Bang. During this time, fusion processes continued as protons and neutrons combined to form the first atomic nuclei. The most abundant elements created were hydrogen, with some fusing further into helium, and trace amounts of lithium. As the universe expanded and cooled, the conditions for fusion were just right to allow these light elements to form. During the era of nucleosynthesis, the temperature of the universe was still extremely high, but it was steadily decreasing. This cooling was critical because it determined when and how the fusion processes could occur. Hydrogen nuclei, or protons, were the first to form, followed by the fusion of some of these protons into helium nuclei. A small fraction of these helium nuclei further combined to create lithium nuclei. By the end of this era, the universe's composition was roughly 75% hydrogen, 25% helium, and tiny amounts of lithium and deuterium nuclei. As the universe continued to cool, it transitioned into the era of nuclei, spanning from 3 minutes to 380,000 years after the Big Bang. During this period, the temperature eventually dropped too low for fusion reactions to continue. This cooling phase marked the end of nucleosynthesis. The universe was filled with a hot, dense plasma consisting of positively charged nuclei and free, negatively charged electrons. These conditions caused photons, or particles of light, to be constantly scattered and trapped within the plasma, preventing them from traveling freely. The era of nucleosynthesis was a crucial time for shaping the chemical composition of the universe. The formation of hydrogen, helium, and lithium during this period set the stage for the development of stars and galaxies. These light elements are the building blocks for all the matter that we observe today. The end of the era of nucleosynthesis and the beginning of the era of nuclei marked a significant transition as the universe moved from a state of high-energy particle interactions to one dominated by atomic nuclei and electrons. The era of atoms, which began around 380,000 years after the Big Bang and lasted up to roughly 1 billion years, marked a significant turning point in the universe's history. As the universe cooled and expanded, conditions finally allowed atomic nuclei to capture free electrons, forming neutral atoms. This process, known as recombination, transformed the universe in a fundamental way. Before the era of atoms, the universe was filled with a hot, dense plasma of charged particles. Photons, or particles of light, were constantly scattered by these particles, unable to travel freely. However, as soon as neutral atoms formed, these photons were no longer trapped. For the first time, light could move freely through space, making the universe transparent. This momentous event allowed photons to travel vast distances, and these ancient photons are what we now observe as the cosmic microwave background. The era of atoms also marks the furthest point back in time that we can observe directly. The period before this era is often referred to as the Dark Ages, because without neutral atoms, there was no light to illuminate the universe. During the Dark Ages, the universe was a sea of invisible particles, and no stars or galaxies had yet formed to light up the cosmos. With the formation of neutral atoms, the stage was set for the next phase of cosmic evolution. Gravity began to draw these atoms together, leading to the formation of the first stars and galaxies. These early structures started to shine, bringing light to the universe and marking the end of the Dark Ages. The light from the first stars began the process of reionization, where the ultraviolet radiation from young stars ionized the surrounding hydrogen gas, creating bubbles of ionized gas that eventually merged to ionize the entire universe once more. The formation of neutral atoms allowed photons to travel freely, creating the cosmic microwave background and making the universe transparent. This era marks the earliest point in time we can observe, bridging the gap between the chaotic early universe and the structured cosmos we see today. The transition from the Dark Ages to a universe filled with stars and galaxies set the stage for the complex and diverse universe we inhabit. The CMB remains a crucial tool for cosmologists, offering a glimpse into the universe's infancy and helping us understand the fundamental processes that have shaped its evolution. This is the story of our universe's beginning. In just a fraction of a second, most of what we observe today came into existence. It's hard to fathom the immense power of the Big Bang and the compactness of that initial singularity. Having explored the origins of the universe, it's now time to delve into an even more intriguing question. How will our universe meet its end? Picture a universe where every star has gone dark, leaving only an endless silence. Galaxies that once teemed with life are now empty and adrift in the vastness of space. As the universe continues to expand, it will eventually run out of energy, leaving everything cold, dark, and lifeless. Even the very fabric of existence will begin to unravel. This is one possible fate of our universe, but there are other theories that are just as plausible. Today, the universe is vast and complex, containing billions of stars, galaxies, and other celestial objects. It's still growing and changing, and scientists are still learning more about its properties. One of the most important things about the universe is its scale. The distances between objects in the universe are so vast that it's hard to even imagine them. Despite its scale, the universe is also delicate. The laws of physics that govern the universe are very precise. And if they were to change even slightly, the universe as we know it would cease to exist. We are reminded of its complexity as we look out into the universe. From the structure of spiral galaxies to the behavior of supernovae, the universe is a complex and intricate system. And yet, despite its complexity, the universe is also a place of uncertainty. There is still much that we don't know about the universe, and scientists are still working to uncover its secrets. The cosmic microwave background is a crucial tool for understanding the universe. It's a type of radiation left over from the early days, detectable everywhere in the cosmos. The CMB was created around 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to form neutral atoms. This marked the end of the Dark Ages, allowing light to travel freely through space for the first time. The CMB is the residual heat from this era, providing a unique window into the past. As the universe continued to cool, the CMB photons changed. The expansion of space stretched their wavelengths, shifting them into the microwave part of the electromagnetic spectrum. This is why we detect them as microwave radiation today. The cooling and stretching of the CMB over billions of years reflect the universe's ongoing expansion and cooling, key aspects of its evolution. These changes not only illustrate the dynamic nature of the universe, but also provide crucial evidence supporting the Big Bang theory. Let us delve into the primary topic at hand, the ultimate fate of the universe. There are several theories proposing the possible demise of the cosmos, and we shall examine each of them, commencing with the Big Freeze hypothesis. As we think about this distant future, we see how fragile and temporary everything is. The universe, huge and old, is like a big cloth made of many threads of matter and energy, each with its own role in the story of existence. But, like everything else, This cloth cannot escape the relentless passage of time. In the eons leading up to the Big Freeze, the universe will undergo many transformations. Stars will continue to burn their nuclear fuel, fusing lighter elements into heavier ones. This process releases energy, which is why stars shine. However, this cannot go on forever. Eventually, stars exhaust their nuclear fuel. For massive stars, this means a dramatic end as supernovae, leaving behind neutron stars or black holes. For stars like our Sun, the end is more subdued. They will expand into red giants, shed their outer layers, and fade into white dwarfs. The remnants of these stars, the white dwarfs, neutron stars, and black holes, will persist for incredibly long timescales. White dwarfs will slowly cool and fade into black dwarfs, emitting no light or heat. Neutron stars, incredibly dense and compact, will remain as dark, cold remnants. Black holes will continue to dominate the cosmic landscape, slowly evaporating over unimaginable timescales due to Hawking radiation. Galaxies, which are currently bustling with star formation, will enter a more quiescent phase. Star formation rates will decline as the gas needed to form new stars is depleted. The once vibrant galaxies will become graveyards of dead stars and stellar remnants. The intricate structures we see in galaxies today, such as spiral arms, will gradually disappear, leaving behind amorphous, dim collections of old stars and remnants. As the universe continues to expand, the energy density will decrease. The cosmic microwave background radiation, the afterglow of the Big Bang, will become even fainter and colder. The wavelength of this radiation will stretch, making it more difficult to detect. The universe, already vast and dark, will become even more so, with the distances between galaxies increasing beyond comprehension. On smaller scales, the cooling of the universe will affect planetary systems. As stars die, their planets will be left adrift in the cold void. Any atmosphere or liquid water on these planets will freeze, and the planets themselves will become cold, desolate rocks. Moons and other celestial bodies will share the same fate, frozen and lifeless. The very fabric of the universe will continue to stretch and cool. Dark energy will drive this expansion, pushing galaxies apart at an accelerating rate. Over time, galaxies will recede from each other faster than the speed of light, becoming unreachable and effectively isolated. The observable universe will shrink as more and more galaxies move beyond our cosmic horizon, the limit beyond which light cannot reach us. In the far, far future, even the most enduring structures will succumb to the effects of the Big Freeze. Protons, the building blocks of atoms, are theorized to decay over extremely long timescales. This process, if it occurs, will cause matter to disintegrate into subatomic particles. The stable structures we know, such as atoms and molecules, will break down, leaving a sea of particles drifting in the dark. Black holes, once thought to be eternal, will also meet their end. Through Hawking radiation, they will slowly lose mass and eventually evaporate completely. This process is incredibly slow, taking longer than the current age of the universe by many orders of magnitude. But given enough time, even the mightiest black holes will disappear, leaving behind a void. As the universe reaches its final stages, it will become a cold, dark expanse. The remaining energy will be spread thinly across an unimaginably vast space. The universe will be dominated by low-energy photons and neutrinos, particles that interact weakly with matter. In this state, all processes that require energy will cease. There will be no more stars, no more galaxies, no more life. The universe will be a vast, empty space with no significant structures remaining. In this bleak, silent cosmos, time will lose its meaning. With no events to mark its passage, the concept of time becomes irrelevant. The universe will exist in a state of maximum entropy, where everything is uniform and unchanging. It is a state of perfect equilibrium, where all energy is evenly distributed and nothing new can ever happen. This is the Big Freeze, the quiet, inevitable end of the universe. It is a final chapter where silence and darkness reign supreme. The universe, once filled with light, warmth, and life, will become a cold, empty expanse. In this distant future, there will be no stars to light the sky, no galaxies to explore, and no planets to call home. The cosmic dance will have ended, leaving behind a still, silent void. Yet, in understanding this fate, we can better appreciate the fleeting beauty of our current universe, cherishing the moments of light and life while they last. The Big Rip is a theory about the end of the universe that proposes a dramatic and violent conclusion to everything we know. Unlike the Big Crunch, where the universe contracts, or the Big Freeze, where it slowly cools, the Big Rip suggests that the universe will be torn apart by the very force that is currently making it expand. To understand the Big Rip, we need to consider dark energy. Dark energy is a mysterious force that makes up about 68% of the universe. It is responsible for the accelerated expansion of the universe. While we don't fully understand what dark energy is, we do know that it has a repulsive effect, pushing galaxies apart. In the Big Rip scenario, the effect of dark energy becomes so powerful that it not only accelerates the expansion of the universe, but also grows stronger over time. In the distant future, as dark energy continues to dominate, it will start affecting gravitationally bound objects. Currently, dark energy affects the large-scale structure of the universe, causing galaxies to move away from each other. However, in the Big Rip theory, as dark energy's influence increases, it will begin to overcome the gravitational forces holding galaxies together. This means that galaxies themselves will start to be pulled apart. The process of the Big Rip can be thought of as happening in stages. The first stage involves galaxies being ripped away from each other. Right now, galaxies are moving away from each other, but they remain intact. In the Big Rip scenario, dark energy will eventually grow so strong that it will tear apart the galaxies themselves. The stars within galaxies will be flung into space as the galaxies disintegrate. As the strength of dark energy continues to increase, the next stage involves the destruction of star systems. Stars and their planetary systems, which are bound together by gravity, will no longer be able to resist the repulsive force of dark energy. Stars will be pulled away from their planets, and planets will be ripped apart. The distances between these celestial objects will grow so vast, and the force pulling them apart will be so great that even the bonds holding planets and moons together will break. The Big Rip doesn't stop there. As dark energy's influence continues to increase, it will start affecting smaller and smaller structures. Eventually, it will become powerful enough to tear apart individual stars. Stars, which are held together by their own gravity, will be unable to withstand the force of dark energy. They will disintegrate, scattering their matter into the ever-expanding void. In the final stages of the Big Rip, dark energy will become so dominant that it will tear apart atoms themselves. The forces that hold atomic nuclei together, the strong and weak nuclear forces, will be overcome by dark energy. Atoms will be ripped apart into subatomic particles, and those particles will continue to be pulled away from each other. The very fabric of matter will disintegrate. The timeline for the Big Rip is vast, spanning billions of years. While it is difficult to pinpoint exactly when each stage will occur, we can outline a general sequence of events. In the initial stages, which are already underway, the universe is expanding at an accelerated rate. Over the next several billion years, this expansion will continue to accelerate. Galaxies will move further apart, and eventually, around 20 to 30 billion years from now, the process of tearing galaxies apart will begin. After the galaxies are torn apart, star systems will follow. This could happen a few billion years after the galaxies start to disintegrate. The destruction of stars will occur even later, perhaps tens of billions of years into the future. Finally, in the ultimate moments of the Big Rip, the very atoms that make up matter will be destroyed, leaving nothing but a dark, empty void filled with isolated subatomic particles. The Big Rip challenges our understanding of the universe and its long-term fate. It paints a picture of a universe that is not just expanding, but accelerating in such a way that it will eventually tear itself apart. This theory suggests that the universe is not a stable, unchanging entity, but a dynamic and ever-evolving one, with a dramatic end in sight. The implications of the Big Rip are profound. It means that the universe will not end in a slow cooling or a gentle fade into darkness, but in a violent and chaotic disintegration. This theory also suggests that the forces we take for granted, such as gravity and the strong nuclear force, are not as permanent as we might think. They can be overcome by the relentless power of dark energy. One of the most intriguing aspects of the Big Rip is the way it changes our perspective on the universe's future. For much of human history, the universe was thought to be static and eternal. The discovery of the expanding universe challenged this view, suggesting that the universe had a beginning and would have an end. The Big Rip takes this idea further, proposing a specific and dramatic end to everything we know. While the Big Rip is a compelling theory, it is important to note that it is not the only possible fate for the universe. Current observations suggest that the universe is expanding at an accelerating rate, but our understanding of dark energy is still limited. Future discoveries could provide new insights into the nature of dark energy and its effects on the universe. These discoveries could confirm the Big Rip scenario, or they could suggest a different fate for the universe. In studying the universe's fate, scientists use a combination of observational data and theoretical models. Observations of distant supernova, the cosmic microwave background, and the distribution of galaxies all provide clues about the universe's expansion. Theoretical models help scientists understand how different forces interact and predict the future behavior of the universe. These models are constantly refined as new data becomes available, and they play a crucial role in our understanding of the universe's fate. The Big Rip also raises philosophical questions about the nature of existence and the meaning of life. If the universe is destined to be torn apart, what does that mean for our place in it? Are we part of a grand cosmic story that will end in chaos, or is there a deeper purpose to our existence? These questions challenge us to think about the universe and our role in it in new and profound ways. The concept of the heat death of the universe describes a scenario where the universe continues to expand and cool until it reaches a state of no thermodynamic free energy and can no longer sustain processes that increase entropy. This theory is based on the second law of thermodynamics, which states that, in an isolated system, entropy tends to increase over time. Entropy is a measure of disorder, and in the context of the universe, it means that the energy available to do work gradually diminishes. The heat death of the universe and the Big Freeze are often discussed together because they describe similar outcomes. a universe that becomes cold, dark, and lifeless. However, there are key differences between these two theories. The Big Freeze focuses on the universe's expansion continuing indefinitely, leading to galaxies drifting so far apart that they are no longer visible to each other. Stars eventually burn out, and the universe becomes dark and cold. On the other hand, heat death considers the implications of entropy, the measure of disorder in a system, and predicts a state where no more energy is available to do work, resulting in a universe that is not only cold and dark, but also in a state of maximum entropy where no processes can occur. In the heat death scenario, the universe's journey towards this final state can be broken down into several stages. Initially, the universe is dynamic and full of activity. Stars form, galaxies collide, and life emerges on some planets. However, these processes are finite and will eventually come to an end. The first stage involves the end of star formation. Stars form from clouds of gas and dust in galaxies. These clouds collapse under gravity, igniting nuclear fusion in their cores, producing light and heat. However, the gas needed for star formation is not infinite. As stars die, they expel their outer layers, but not all of this material is recycled into new stars. Some of it is lost to space. Over billions of years, the rate of star formation will decline. Eventually, there will be no new stars forming, and the existing stars will gradually burn out. Stars have a finite lifespan. Small stars, like our Sun, will expand into red giants and then shed their outer layers, leaving behind a white dwarf. Massive stars end their lives in supernova explosions, leaving behind neutron stars or black holes. White dwarfs and neutron stars will cool and fade over time, becoming cold, dark remnants. Black holes will persist for longer, but even they are not eternal. Black holes slowly lose mass through a process called Hawking radiation. This radiation, named after physicist Stephen Hawking, is a theoretical prediction that black holes emit small amounts of radiation due to quantum effects near their event horizons. Over incredibly long timescales, black holes will lose mass and eventually evaporate completely. This process takes longer than the current age of the universe by many orders of magnitude, but it is an essential part of the heat death scenario. As stars burn out and black holes evaporate, the universe will become a dark, cold place. The remaining matter will be in the form of subatomic particles and low-energy radiation. These particles will be spread thinly across an ever-expanding space, and the average temperature of the universe will approach absolute zero, the point at which all thermal motion ceases. In this final state, the universe will be in thermodynamic equilibrium, meaning there will be no energy gradients to drive processes that increase entropy. All physical processes will have ceased, and the universe will be static and unchanging. This state of maximum entropy is what is referred to as the heat death of the universe. The timeline for reaching heat death is staggeringly long. Current estimates suggest that star formation will cease in about 100 trillion years. White dwarfs will take longer to cool and fade, potentially up to a quadrillion years. Black holes will take even longer to evaporate, on the order of 10,100 years. After this point, the universe will consist mostly of low-energy photons and neutrinos, particles that interact very weakly with matter. As the universe continues to expand, the distances between particles will increase, and any remaining interactions will become exceedingly rare. The universe will be a vast, empty expanse with no significant structures. The process of expansion will continue indefinitely, driven by dark energy, until the universe reaches a state where all remaining particles are isolated from each other by immense distances. The heat death scenario presents a stark and sobering picture of the universe's future. It suggests that the universe will end not with a bang, but with a whimper, gradually fading into darkness and silence. This theory raises profound questions about the nature of time, existence, and the ultimate fate of the cosmos. One of the key aspects of the heat death scenario is the concept of entropy. In everyday terms, entropy is often associated with disorder or randomness. In thermodynamics, entropy is a measure of the number of ways a system can be arranged, with higher entropy corresponding to more possible arrangements. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time. This means that the universe is constantly evolving towards states of higher entropy. The increase in entropy is a natural consequence of the universe's expansion. As the universe expands, the energy within it becomes more spread out, and the overall temperature decreases. This spreading out of energy leads to a more disordered state with higher entropy. Over time, the universe will reach a point where it has maximum entropy, and no more work can be done. This is the essence of the heat death scenario. Another important concept in the heat death scenario is the role of dark energy. Dark energy is the driving force behind the accelerated expansion of the universe. It was first discovered in the late 1990s through observations of distant supernova, which showed that the universe's expansion was not slowing down, as previously thought, but was instead accelerating. This discovery was surprising and led to the realization that dark energy makes up a significant portion of the universe's total energy density. The nature of dark energy is still not well understood, but it is thought to be a property of space itself. As the universe expands, more space is created, and with it, more dark energy. This means that dark energy will continue to drive the universe's expansion indefinitely, leading to the eventual heat death scenario. The heat death of the universe is a concept that can be difficult to fully grasp due to the immense timescales involved. Human history spans only a few thousand years, and the current age of the universe is about 13.8 billion years. The timescales involved in the heat death scenario are many orders of magnitude longer than anything we can easily comprehend. However, by studying the universe and its long-term evolution, scientists can gain insights into its ultimate fate. The heat death scenario also has implications for the search for extraterrestrial life. If the universe is destined to end in a state of maximum entropy, then life, as we know it, is a temporary phenomenon. Life requires energy to sustain itself, and in a universe heading towards heat death, the available energy will gradually diminish. This means that life, if it exists elsewhere in the universe, is likely to face the same ultimate fate as life on Earth. The heat death scenario also raises philosophical questions about the meaning of existence and the nature of time. If the universe is destined to end in a state of maximum entropy, then what does that mean for the significance of our lives and the events that take place within the universe? These questions challenge us to think deeply about our place in the cosmos and the nature of reality. The Big Crunch is a theory about the ultimate fate of the universe, presenting an intriguing counterpoint to the concept of the Big Freeze. In the Big Crunch scenario, the universe, instead of expanding forever, will eventually reverse its expansion and start to contract, leading to a final collapse. This theory is both fascinating and a little daunting, as it challenges our understanding of the universe and its long-term destiny. To understand the Big Crunch, we must first consider the forces at play in our universe. Since the Big Bang, the universe has been expanding. Galaxies are moving away from each other, and this expansion is driven by dark energy, and it acts as a kind of anti-gravity, pushing galaxies apart. For the Big Crunch to occur, the influence of dark energy would need to diminish, and gravity, the force pulling matter together, would have to dominate. Gravity is the attractive force that pulls objects with mass toward each other. On a cosmic scale, gravity pulls galaxies, stars, and planets together. If the expansion of the universe were to slow down and eventually stop, gravity would begin to pull everything back together. This would mark the beginning of the end, as the universe would start to contract. In the early stages of this contraction, galaxies would begin to move closer to each other. The vast stretches of empty space between galaxies would shrink, bringing cosmic structures into ever closer proximity. This contraction would be slow at first, almost imperceptible over human timescales, but it would gradually accelerate. As the universe contracts, galaxies would collide and merge, forming larger and larger structures. These galactic mergers would be chaotic and violent, as stars and planetary systems would be thrown into disarray. The gravitational interactions would lead to the formation of massive black holes at the centers of these merged galaxies. These black holes would grow in size as they consumed stars and other matter, becoming the dominant features of the contracting universe. Stars, the bright beacons of light in the cosmos, would face a grim fate. The increased density of matter would lead to more frequent stellar collisions, resulting in massive explosions known as supernovae. These explosions would temporarily light up the darkening universe, but they would also mark the death of stars. Over time, fewer and fewer stars would remain, and the universe would become increasingly dark. Planets, too, would be affected by the cosmic contraction. As stars die and black holes grow, planetary systems would be disrupted. Some planets might be ejected into interstellar space, becoming rogue planets, while others would be pulled into the growing black holes. The delicate balance that allows for stable planetary orbits would be shattered, leading to the end of habitable conditions. As the contraction progresses, the temperature of the universe would begin to rise. The energy released from the collisions and mergers of galaxies, stars, and black holes would heat up the cosmic environment. This increase in temperature would accelerate the contraction, creating a feedback loop where higher temperatures lead to faster collapse. In the later stages of the Big Crunch, the universe would become a hot, dense, and chaotic place. The distances between remaining objects would shrink further, and the density of matter would increase dramatically. Black holes would continue to merge and grow, eventually consuming most of the matter in the universe. The sky would be filled with the intense radiation from these mergers, making it a hostile environment for any remaining structures. As the universe approaches its final moments, the contraction would reach a critical point. The density and temperature would become so extreme that the very fabric of space-time would begin to warp. At this stage, the distinction between different objects would blur, and the universe would start to resemble the conditions of the Big Bang, but in reverse. In the ultimate moments of the Big Crunch, all matter and energy would converge into a single, infinitely dense point known as a singularity. This singularity would be similar to the state from which the Big Bang originated, but instead of expanding, it would signify the end of the universe as we know it. The laws of physics as we understand them would break down in this singularity, making it a realm beyond our current comprehension. The Big Crunch poses many questions about the nature of the universe and its cycles. Some theories suggest that the universe could be cyclic, undergoing endless cycles of expansion and contraction. In this view, the Big Crunch could lead to a new Big Bang, starting the process of creation all over again. This idea, known as the Big Bounce, suggests that the universe is eternal, constantly renewing itself through cycles of birth, death, and rebirth. The concept of the Big Crunch also raises philosophical and existential questions. If the universe is destined to collapse and restart, what does that mean for the meaning of life and existence? Are we part of an endless loop, or is there a deeper purpose to the cosmic cycles? These questions challenge our understanding of time, existence, and the nature of reality. While the Big Crunch is a compelling theory, it is not the only possible fate of the universe. Current observations suggest that the universe's expansion is accelerating, driven by dark energy. If this acceleration continues, the Big Freeze, where the universe expands forever and becomes cold and empty, is a more likely outcome. However, our understanding of dark energy is still limited, and future discoveries could change our perspective on the universe's fate. The study of the universe's ultimate fate is an ongoing endeavor, combining observations, theoretical physics, and cosmology. Advances in technology and new observations could provide insights into the nature of dark energy, gravity, and the fundamental forces that govern the cosmos. These discoveries will help us refine our theories and deepen our understanding of the universe's long-term destiny. The idea of the Big Crunch also emphasizes the dynamic and ever-changing nature of the universe. The cosmos is not static. It evolves over time, shaped by the interplay of forces and matter. From the birth of stars to the formation of galaxies, and potentially to the ultimate collapse, the universe is a complex and dynamic system. This perspective invites us to appreciate the beauty and complexity of the cosmos, recognizing that we are part of a vast and intricate cosmic story. In contemplating the Big Crunch, we are reminded of the impermanence of all things. The universe, with all its wonders and mysteries, is on a journey that may one day lead to its collapse. Yet, this understanding also brings a sense of wonder and awe. We are part of a grand cosmic narrative, one that spans billions of years and encompasses the birth and death of stars, galaxies, and perhaps the universe itself. As we continue to explore the universe and seek answers to these profound questions, we are driven by curiosity and a desire to understand our place in the cosmos. Whether the universe ends in a Big Crunch, a Big Freeze, or some other fate, the journey of discovery is a testament to the human spirit and our quest for knowledge. In studying the universe, we not only learn about the cosmos, but also about ourselves and our connection to the greater whole. The cosmic cycle, a fascinating concept that has garnered significant attention in the realm of astrophysics and cosmology. The idea proposes that our universe undergoes an eternal cycle of expansion and contraction, with each cycle giving rise to a new universe. The concept of the cosmic cycle was first proposed by astrophysicists Paul Steinhardt and Neil Turok, along with string theorist Berta Vroet. They imagined an oscillatory cosmos in which our brain, a higher dimensional surface, repeatedly collides with a neighboring brain. This collision infuses energy into our universe, driving its expansion and giving rise to the structures we observe today. Each cycle wipes out the previous one, with new structures forming from the energy released during the collision. The researchers drew inspiration from string theory, which posits that the universe is composed of strings and brains. The vibrations of these strings give rise to the particles we observe, while the brains provide the framework for our universe. The collision between brains is thought to occur in a higher dimension, with our universe being a four-dimensional region on one of these branes. The cosmic cycle theory offers an explanation for several features of our universe, including the formation and distribution of galaxies, as well as the acceleration of three-dimensional space. The energy released during the brane collision is thought to be the driving force behind this acceleration, which we observe as dark energy. One of the most intriguing aspects of the cosmic cycle theory is its implications for the ultimate fate of our universe. According to this theory, our universe will eventually come to an end, but not in the sense of a catastrophic event. Instead, it will slowly wind down, with all matter and energy being drained away. This process will continue until the universe reaches a state of perfect uniformity, devoid of any structure or energy. However, this is not the end of the story. The cosmic cycle theory proposes that this state of uniformity is identical to the state of the universe at its beginning. Through a process known as conformal transformation, the universe can be reborn, with degraded particles becoming vibrant once more. This means that the demise of our universe becomes a new beginning, with the cycle repeating itself ad infinitum. The concept of the cosmic cycle has been explored in greater detail by researchers such as Roger Penrose, who has developed the theory of conformal cyclic cosmology. This theory proposes that the universe undergoes an infinite series of cycles, with each cycle giving rise to a new universe. The theory is supported by the idea that the universe will eventually reach a state of maximum entropy, at which point it will undergo a transformation, giving rise to a new cycle. Dark matter and dark energy have been explored before, but now let's delve into each one more closely. In the vastness of space, there are two mysterious forces that hold the secrets to the universe's fate: dark matter and dark energy. These unseen forces are both creators and destroyers, shaping the cosmos in ways we are only beginning to understand. Dark matter is like an invisible glue that holds galaxies together. It's all around us, but we can't see it or touch it. We know it's there because of its powerful pull on the things we can see, like stars and planets. Without dark matter, galaxies wouldn't have formed in the first place. Stars wouldn't have gathered to create the light we see in the night sky. In this way, dark matter is a creator, building the structure of the universe and allowing stars and planets to exist. But there's another force at work, pushing everything apart: dark energy. While dark matter pulls things together, dark energy pushes them away. It's causing the universe to expand faster and faster. This means galaxies are moving away from each other, and the spaces between them are getting bigger. Over time, this will lead to a universe where galaxies are so far apart that their light can't reach each other. The night sky will become darker and emptier. As dark energy continues to push the universe apart, the stars within galaxies will eventually burn out. When the fuel that powers them is gone, they will die, leaving behind cold, dark remnants. Planets will become frozen wastelands. The once bright and lively universe will turn into a cold, dark place. In this way, dark energy acts as a destroyer, driving the universe towards a lonely, empty end. But the story of dark matter and dark energy is not just about endings. It's about the balance between creation and destruction. Dark matter creates the conditions for galaxies, stars, and planets to form. It builds the universe we see and know. Dark energy, on the other hand, yours that this creation is not permanent. It pushes the universe towards its eventual end, stretching the fabric of space and making everything drift apart. Imagine a cosmic dance where dark matter and dark energy are partners. Dark matter leads, pulling galaxies together and forming stars. Dark energy follows, gently nudging everything apart, ensuring the dance doesn't go on forever. Together, they create a universe that is always changing, always evolving. As time goes on, dark energy's influence will grow stronger. It will overpower the pull of dark matter, leading to a future where galaxies can't hold together. Stars will drift away from each other, and the universe will become a vast, empty expanse. The structures that dark matter created will slowly break apart, leaving behind a cold, dark void. In the end, the universe will be a dark, empty place. The galaxies, stars, and planets that dark matter helped create will be spread thin, isolated in the vastness of space. Dark energy will have done its work, pushing everything apart until there is nothing left but darkness and cold. Part A. At the very beginning, the universe was governed by the laws of quantum mechanics, which are very different from the classical laws of physics that we experience in our everyday lives. In the quantum realm, particles do not have definite positions or velocities, but instead exist in a state of probabilities. This means that particles can appear and disappear randomly, and they can exist in multiple places at once. One of the most intriguing phenomena in quantum mechanics is quantum tunneling. In classical physics, if a particle encounters a barrier that it does not have enough energy to overcome, it will simply be reflected back. However, in quantum mechanics, there is a probability that the particle can tunnel through the barrier and appear on the other side, even though it does not have enough energy to do so in a classical sense. In the context of the early universe, quantum tunneling could have played a crucial role in the transition from the singularity to the Big Bang. The early universe may have been trapped in a high-energy state, often referred to as a false vacuum. A false vacuum is a local minimum of energy that is not the lowest possible energy state, meaning that there is a more stable, lower energy state available. Quantum tunneling could have allowed the universe to escape from this false vacuum state by tunneling through the energy barrier that separated it from the true vacuum, the lowest energy state. This tunneling event would have released a tremendous amount of energy, leading to the rapid expansion and cooling of the universe, known as cosmic inflation. During this inflationary period, the universe expanded exponentially, smoothing out any irregularities and setting the stage for the formation of galaxies, stars, and planets. The end of the universe. Just as quantum tunneling may have played a role in the birth of the universe, it could also influence its ultimate fate. There are several scenarios for how the universe might end, and quantum tunneling features prominently in some of them. One potential scenario involves vacuum decay, a process that is intimately connected to quantum tunneling. As mentioned earlier, our universe might currently be in a false vacuum state. If this is the case, then there is a small but non-zero probability that quantum tunneling could cause a transition to a true vacuum state. If such a transition were to occur, it would start with a tiny bubble of true vacuum forming somewhere in the universe. This bubble would then expand at the speed of light, consuming everything in its path. The energy released in this process would alter the fundamental constants of nature, effectively rewriting the laws of physics. Life, as we know it, would not be able to survive this transition, making vacuum decay a catastrophic event. Another way quantum tunneling could influence the end of the universe is through black holes. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. According to quantum mechanics, black holes are not completely black, but emit a faint radiation known as Hawking radiation. This radiation is a result of quantum effects near the black hole's event horizon. the boundary beyond which nothing can escape. Hawking radiation causes black holes to lose mass and energy over time. Eventually, black holes could evaporate completely due to this radiation. While the timescales for this process are incredibly long, far longer than the current age of the universe, the evaporation of black holes could contribute to the ultimate fate of the universe by returning their energy to the surrounding space. In the distant future, as stars burn out and galaxies drift apart, the universe might approach a state of maximum entropy, often referred to as the heat death or big freeze. In this scenario, the universe continues to expand, and matter becomes increasingly sparse and cold. Quantum tunneling could still play a role in this era, as particles and radiation slowly interact and decay over time, gradually moving toward a state of perfect uniformity and low energy. While these ideas about the end of the universe are still theoretical, they highlight the profound impact that quantum tunneling can have on cosmic events. The same principles that allow particles to tunnel through barriers in laboratory experiments could govern the fate of the entire universe. So this is how our universe might meet its end. These theories represent our current understanding, but there could be unexpected reasons beyond our imagination. No matter what, we won't be around to witness it. For now, we can only contemplate the theories our minds can comprehend, though the universe's mysteries extend far beyond our grasp. And with that, we conclude this video. I hope you enjoyed it. If you did, please give us a like and subscribe.